My name's Fritz Klassner. I'm the Natural Resource Program Manager with the Office of Maunakea Management. Thank you all for coming tonight. This is the Maunakea Speaker Series, which is a partnership between Imiloa Astronomy Center, the Hilo Physics and Astronomy Department, which is the building that we're in tonight, and Office of Maunakea Management. And the focus of the Speaker Series is really about the scholarship and some of the work that's being done about Mauna Kea, not so much on Mauna Kea, but about Mauna Kea. And to that end, tonight, of course, is the Maunakea Weather Center, which we'll get to talk a little bit more about in a minute. Just a brief introduction of Ryan Lyman. Ryan is a Hilo native, Kamehameha Schools grad, got his, actually, University of Hawaii Manoa, bachelor's and master's degree in meteorology. He's been the forecasting meteorologist at the Maunakea Weather Center for past 15 or so years, if my memory is correct. And just as an aside, you know, what I find unique about the Maunakea Weather Center forecast is they're one of the only places that I know of that actually publish their accuracy statistics. You have to kind of dig down and look. But most places, we all complain about the weather, and if you want nice weather at the summit of Mauna Kea, this is the guy to ask to change the forecast, because it's pretty accurate. It's really darn accurate, but no, what's really novel about it, in my experience, is if you have to go through the research papers and the archives of the site, but they publish their accuracy statistics. They say what they're trying to shoot for, and they say how good of a job they're doing, how that's evolved over time. And in my experience, that's a really novel sort of feature of any kind of weather forecasting service, is to share their weather forecast. Personally, I use it. One of my passions is climate change. If you've been listening to the news, North Pole is about 45 degrees above normal. There's a website called yr.no. It's the Norwegian National Weather Service. And right now, Sunday is supposed to be warmer at the North Pole than the summit of Mauna Kea. If that happens, we'll be doing a social media post about that. Been waiting for that, watching that for a couple of years. But they're using the forecast data and the weather data that the Maunakea Weather Center makes available. It's used not only here in Hawaii, but it's used internationally, and there's some, that my sort of trivial pursuit climate change issue is a one-off and event kind of thing. But it's the point being, it's used internationally and known internationally. And with that, thank you, Ryan, for coming tonight. Appreciate it.
Thanks, Fritz. Thanks, Fritz, for that. About talking about how statistically we are. I mean, it's actually kind of funny because when everybody talks about me, all my friends, they only talk about how I get it wrong all the time, and that's kind of indicative of what the title's about, more than just passing showers. And we don't forecast that for the summit. And this picture here is it's kind of how I got into meteorology. This picture of Bayfront soccer fields. Sure. Picture of Bayfront soccer fields. If you're looking from Ben Franklin towards the ocean, and I got into it because I was interested in flash floods as a kid, and actually my meteorology. Yeah, so I got into meteorology through forecasting flash floods, actually, quite a bit, and it's actually the timing of me stepping into the meteorology for the Maunakea Weather Center as a forecast meteorologist was actually quite well. I just got finished up with my master's. Somebody else was leading the site as a forecast meteorologist, and I kind of slid right in through graduate school. And it actually worked out quite well because being born and raised here, I got to move home. As a meteorologist, it's a unique position. Most meteorologists are situated throughout the United States, or they're traveling, or they're going through the Air Force. Actually, being a meteorologist in Hilo is unique. I don't think there's anybody else here unless they're a technician. Just a brief background about Maunakea Weather Center. Everyone here familiar with the site? Or, I mean, I know Mark is, of course, and Don. I'm not sure if most people aren't, I assume. Okay. Well, just a brief background. Maunakea Weather Center started in 1999 as a collaboration between SOES and US UH Manoa. SOES is like the meteorology department, geophysics department up there. And it was created to create custom forecasts for Mauna Kea observatories because they were in such need. National Weather Service was providing just basic forecasting partly showers, partly snowing kind of forecast. And they're needing something a little bit more than that. If you talk to Mark, he was in kind of on the ground zero on that as well, talking about how to get custom forecasts for Maunakea so that they can get better scheduling of how they're going to run throughout the night and so forth. And I'm hoping Mark will talk about that next time. I don't want to get into that too much. But our primary focus is to for Maunakea Weather Center to issue daily forecasts. We do this twice a day, 10 and 5 p.m., Monday through Friday. We consolidate all the weather data that comes into various sources, and I'll talk about them all in a bit. I'll put them all on one page for everybody to use. We maintain the data flow of global models, which will just kind of project what the data is going to be or what it's going to be like. And then we also run a mesoscale model off of that looks specifically at the sun. I'm just briefly going over this. This is the amount of data that we get in. It's actually on the order of like, I want to say 100 gigabytes a day. They all go in through our different servers, processed, and then posted. Where is this one? Yeah, on our main MKWC server. I'll go through a few of our products in a bit. But we've got like three servers running. We've got clusters in the background that run our mesoscale models that actually makes it more of a higher resolution of what's going on at the summit. We got backup servers. These are the blue over here is this amount of data flow that comes in, and it all gets posted for just one site for simplicity. Some of our products that we offer are just the current conditions of the summit, including webcams, the road conditions, what the observations are for each observatory. We also have the remote sensors, satellite, and radar. I'll kind of go through all of these in a bit. Our global models, and of course, our mesoscale model, and of course, our forecast. It's just a brief, well, this is what our current conditions were this morning. So this table here just shows what each observatory was reporting at that specific time. So I think this is at 10:50 in the morning. It has our temperature, dew point, wind speeds, all the basics. Basically, it flags different colors when we're getting less than optimal conditions. In this case, it was high humidity. And if you guys look at the site, you can see that this is pretty much socked in. We also have wind bars here showing what it is for each observatory site. Over here being CPHT and Gemini, and looping down into UAG and then down on the bottom. Consolidate all webcams, have it easily available for everyone. We also show what the road is like, so there's an interactive map. Basically takes all that data and puts it on here. So this is, as you're going up to CPHT, it shows, and it also flags it when we got bad conditions. What the wind's like, if ice is detected on the road. All of this is on there. It's an interactive map too. Like if you were to go onto this site and you scroll over certain, like the gray triangles, it'll show you what the webcams are like. All of those things are posted there. In addition to that, we're kind of moving towards having this more interactively displayed by showing what's going on in each specific site. So if you're looking up at the road, we'll display when the road is closed, and that'll be collaborating with the rangers, hopefully in the future. One of the things that we do have in order to do this is ice sensors. We're installing ice sensors. Right now, there's one installed at UCART that basically points at the road. And we're actually in the progress of installing 2 more ice sensors that allow for safety on the road and when to display road closures. It's kind of, all of these things, all of these sites is all maintained by me. I do most of the maintaining of these products, all the data flow, the forecast, all of those things. And we do this constantly. I write programs to do it, write scripts to do this, and it's at the point of it's doing on its own. And then one of the other things that I also do is maintain this ice sensor. Basically, it's just it's a laser that sits at UCART and points down at this road and reports what's going on. It can tell us anywhere between if we have ice on the road, black ice on the road, snow on the road. And it's a safety measure, but it also allows us to determine, should we go up or not? Well, the astronomers or the engineers. It also is a pretty good indicator of fog, and we can use that to validate our forecasts. We also display the seeing monitor. Everyone, I assume most people aren't familiar with seeing, aside from, I mean, that's Mark's right there, yeah. But we display what the seeing is, and actually a lot of this stuff was helped with collaboration through Mark. And I'll go into this in a bit. SKUT diagrams is also posted on our site, is basically to see what the stability of the atmosphere is. I use this daily, and I'm kind of going to dig through this real quick because I talk about it a little bit more in the future. But basically, so Hilo, the Hui, they launched radioton balloons up in there. Most of you have probably seen this before, and it basically takes measurements throughout the atmosphere. You know, it takes the temperature, pressure, wind speeds, dew point, and it just basically maps out the vertical in the atmosphere. So in this, we have the dew point temperature is the blue dashed line, and the red is the ambient air, the air temperature. This here is in June of 2017, and a fairly typical conditions for Hilo. So this green line here depicts the summit, and what we have is here is this where the blue and the red kind of separate from each other. It's known as the trade inversion. And what makes Mauna Kea so great for observing is that because above this, the air mass tends to be really quite dry. Unlike today, where we have these two lines really close together all the way up, it shows that the atmosphere is saturated. That's really stable and poor for observing, and in this case, cloudy as well. Other things we display is what precipitation is like for each site. If you kind of scroll through these sites, you'll display how much rain fell over the last 24 hours. And this changes, I think this changes hourly. So in a satellite we display water vapor, infrared, and visible imagery. And this has a resolution of about anywhere between 1 to 8 kilometers. The geostationary satellite just sits over our area of the Pacific and just shoots down and just gives us an image in various wavelengths. We also display polar satellites, which is revolved around the Earth, take snapshots. Difference between that is that it has increased sensitivity, so it allows us to derive certain aspects of the atmosphere. But the problem is that it only takes images every, like 4 times a day. So this geostationary satellite is what we rely on quite a bit to show what's going on, how the weather is evolving over the past 24 hours, 48 hours or so. This image right here is the infrared satellite image goes west from this morning, all the way through into last night. So you can see that in this case, it's basically just measurement of the top layer cloud. Over here, it's really cold tops, so it's indicative of high clouds. Pretty much all of us all over the state, where it's got this deep red clouds right here, and here is indicative of thunderstorms or convection. And in this case, it's poor observing for us. Well, very poor. And actually, it's not as bad as last week because most of it is stratiforming, but it's still nonetheless we saw it would fall. Another tool that we use is the WSTAR-88Ds. Basically, just radars. They're the old radars from 88 stands for 1988. That's how old they are. They weren't installed in 88, but they're pretty much old hardware. We have 4 radars situated throughout the state. One in Lehui, one in Molokai, one in Nahel, and another one in Kamuela. They have high temporal resolution. We can get snapshots of what the precipitation is like every 5 to 6 minutes from each of the sites. The spatial resolution is really tight as well. It's great to derive products such as precipitation, winds, liquid water. There's a lot of things we can do with it. But problem is there's a lot of limitations due to mountain blockage, attenuation, its position, which is a problem from FAA, how they decided where they put it. I'm not going to get into that, but you'll see it in a bit. I'm disappointed with where things are, particularly for Hilo and Kona. And then there's forced blackout regions, due to the sun. That's another hope, just so that they don't. There's no what am I call it? Problems between the certain wavelengths and the interference. And so there's poorly indicated weather in certain areas, particularly the summit. Well, that's because they wanted it that way, but that's fine. And you can see it. You can see the mountain blockage quite clear. So this is the radar from this morning. Radar image. Yellow denotes pretty much heavier rain. As you get into red, it's really heavy. Purple, you're getting hail. Green is shadow forming. So the radar on the left is a Nalu radar, and you can see its effect. I mean, we all seen what the satellite was from this morning. They're socked in. Well, over here is showing that it's got clear skies to the northwest. Obviously not the case. This is the Conwell radar, and it shows clear skies to the north. So it's clear you can see the mountain blockage. Still, it's great for us to see what's coming in and how weather is evolving. If they're going to get fog coming in certain instances, it's still useful for me to forecast. Another thing we maintain is this global forecast model. So this is a model that, a mathematical model that shows what the weather is like going to be up throughout the entire world. It's run 4 times a day, 2 and 8, 2 and 8 again, AM, PM, which is the same as 0 and 12 UTC. And it forecasts out to 16 days. Obviously, the further you go in the forecast, the accuracy becomes less and less. It has a 25 kilometer horizontal resolution, and in the beginning hours, and as we go off into the further hours, 14 days, that resolution increases. And it takes snapshots of certain variables throughout 64 layers of the atmosphere. This model started out as I want to say 1 kilometer, 100 kilometer resolution, and gradually decreased the time as it evolved. It has a temporal resolution of as high as an hour, but we only post every 6 hours. That way, data flow we just start to exponentially grow, and it's not entirely useful. We displayed the entire Pacific and with the emphasis on the state of Hawaii. I just can't run that model to go for the entire world. And like I said, we only forecast for Maunakea, so there's no point in that. We display various meteorological variables: temperature, winds, precipitation, everything. That evolves, that is useful for the sun. So here's just an example. So this is the West Coast. This is Japan here, and this is the precipitation field of what we expect over the next 7 days. So Hawaii is right here in the middle, wherever the green blob is. And it starts out, I can't skip it forward, but it starts out us getting socked in and then gradually improving, at least for our portion of the state, where all the thunderstorms start to evolve and move westward as the time goes on. That's the most simplest thing, but I also do it for humidity. So this is 600, same graph, just different, 600 millibar relative humidity. If you refer back to the QT chart, 600 millibar is roughly the height of the sun. And I use this to see, okay, is there going to be fog, or what's the humidity like for the sun? Obviously, they want more dry conditions. This shows a lot. The white is white, green, blue, white, green, and green is pretty bad. We want blue right there. And normally it is blue. I want to say 25% of the year it comes like this, but normally like 75-80% of the time it's very good shape and ready to go. Everything's dry. We've been in the wet spell over the last month. I'm sure Sean will start complaining again, but he's to me, but I can't do anything about it. This is that same diagram I showed earlier, QT diagram. So basically, same thing. I use that GFS model, and I get temperature. I take one grid point right over the summit or right near the summit, and I extrapolate all the data from that one grid point, down from 1,000 millibars of the surface all the way up to the tropopause. And we use that to create, a profile of what's going on at that point, where we get all the winds. And all the winds, we get the temperature, we get the how saturated the air mass is, and we show it over time. And in this case, it's the atmosphere starts out saturated and then slowly dries out at the end. And then this is used to help derive the forecast. A lot of this data that I just went through gets ingested into what is referred to as the mesoscale model of WRF. This is run by my colleague. She's now in Unity. She does both. She does it in Unity and Android, and she does it remotely. She runs the WRF and ingests all this data that I just dumped in there, plus observations, and puts it in there, and we shoot out a mesoscale model to map out what's the weather going to be like out at the summit and the surrounding waters. The benefit behind this is it includes other variables that can't be ingested into the global model, such as terrain. GFS until recently hasn't had a good handle on how to ingest the terrain in there. So instead of us now being a flat surface, prior to maybe 10 years ago, the global model would just look at us as just being ocean. Now it's looking at us as being a little rocky ocean. You know, that doesn't have us at 4 kilometers of what the summit's at, but I mean, it's still done better than what it's now. But the mesoscale model will include various terrains, what kind of coverage they have, whether it's grass, whether it's, you know, lava fields, whatever. They'll have that in there, and it accounts for that in the model. And it's used particularly to judge small-scale perturbations both in time and space, and in particular turbulence in the free atmosphere, which is where this paper's presentation is going. Just brief some of the work domains. We have 4 domains we use, and they're really fine-tuned. If you remember correctly, the horizontal domain of resolution of the GFS is 10 kilometers. Well, we pump that down all the way to 300 meters. We take all that, and it allows us to see what's going on at this up at the summit. Right now, we post every 3 hours, but we can squash this down to minutes when we get into research work. Here's what our domains look like. Here's like just the Central Pacific, and then we get in. We just focus in on the Hawaiian Islands, and there's actually a subdomain in there, and that's used for log forecasting. A lot of our stuff goes back into another cluster, and they use it to see what's going on with the log. And then we have this 300-meter forecast where we look at just the sun. All of this is used to create our forecast, and this is my primary job, although I get sidetracked numerously like everyone else. But I issue these forecasts twice a day, mostly out of my house, just because for convenience, but occasionally through the dungeon and IFA. This is done at 10 a.m. and 5 p.m. every day, Monday through Friday. We issue forecasts for fog, ice, precipitation, and cloud cover and cloud height. We look at temperature, and winds, and precipitable water. Now, precipitable water, if you're unfamiliar with that, is basically I take a column of my air and from my surface, wherever my surface may be. If I'm like right here in Hilo, and I go all the way to the top of the troposphere, how much water did it break? How much water can I extract out of that column? That's precipitable water. And they need that to determine if they're going to observe that wavelength or not. We also look at atmospheric turbulence or seeing, and I'll talk about that again, and then I give a discussion. What's going on? Where is the ridge? Where's the front? All of these things are all embedded in the forecast. Typically, the GFS is used for the construction of the forecast. I use that as the basis. And especially for the key summit variables, temperature, precipitable water, all of those. And I know there's a bias for all of it. After doing this for 15 years, and my predecessors before that, we've been able to figure out what biases the models have. And they've got quite a few. And I'll show you, like, for a quick example. And then we use WRF to look at find small-scale perturbations and use that between the other things that need to can't be resolved through the GFS, particularly C. So as an example, here's like a trend or a time series of the key summit variables at the summit as a function of time. So this is today. So this started out this morning at 2 a.m. and it goes Friday, Saturday, Sunday, all the way out to next week, Thursday. This first subplot here is the temperature. This is what the GFS has. It dumps it out. What the ambient air temperature is at 600 millibars. What the humidity would be like over the course of that period. What the precipitable water and the wind speeds. So, for example, temperature, these are the biases. It tends to overestimate the temperature just a touch, maybe like a degree or so. And that number gets highly skewed when winds are high. So if I get 50 mile-per-hour winds and it's telling me I'm getting 0 degrees, I drop that down always to -5 degrees, for example. It also doesn't take into account the diurnal fluctuations. Right there, it shows you that it doesn't take into account the terrain, which causes the diurnal fluctuations. We all know that it's like at night it's cooler than the day. Not shown here. These little dots coming in and down and out is basically just showing the stability of the atmosphere. Humidity, same thing. It doesn't show that diurnal fluctuation, but it's fairly accurate under most conditions, as well as precipitable water. And just as a side note, precipitable water, we prefer it to be like close to 1 to 2 millimeters, preferably below 1 millimeter, and right now it's forecasted to be 15 millimeters. So that's really radiation out of saturated atmospheres. And then wind speed tends to underestimate just a touch, but when you get into high winds, it could say 50 miles an hour, and I've seen it go up to 150 miles an hour up to the summit. So it doesn't, the variability of different topography and buildings are missing as well. Obviously, it can take into account missing buildings, but topography it could a little. Here's the same graph, but the 200 millibar relative humidity, 250 millibar, and 300. And I use this to indicate cloud cover and cloud height, in addition to precipitable water. And this is pretty accurate as how I've used the forecast. So I talked about precipitable water real quick earlier. This graph here shows the percentage of time fog occurs, so 0 to all the way to 100%, as a function of the GFS precipitable water between 700 millibars, which is the height of high block, to 500 millibars. What we find is that the percent that fog occurs is linearly correlated. So as that value goes up, so does the percentage chance of fog. So this is 0% and roughly 0 millimeters within that layer, and all the way up to 1 millimeter. As we get up to 1 millimeter, pretty sure chances of fog is going to increase significantly. So I mean, those are examples of just using the GFS to figure out how we're going to forecast. All of this, it pumps in, and after working and massaging the data, I create this morning forecast. So this graph here is displayed on our forecast page, and each subplot, so this is a function of time again, so this is from this morning, I believe. This is this morning's forecast. So this is Thursday, this is tomorrow, Saturday, Sunday, Monday, and then Tuesday. I issue a 5-day forecast. The first subplot here is the percentage chance of fog or precipitation and precipitation. Red is precipitation, blue is fog. This is the cloud cover and cloud height forecast. This is temperature, precipitable water, seeing, and winds. And then this graph is probably one place you need to go if you want to know what the forecast is, without having to dig through and read all my journal that goes on over there. This will give you a snapshot of what's going on real quick. And as you can see, they're pretty much locked in again. I'm calling for 100% chance of fog all the way through Saturday night, and then gradually decreasing. Seeing though, what is seeing? That's the difficult part, and that's what the rest of this presentation is going to cover. Forecasting seeing has always been the challenge, and it's something that I still listen to Mark. The first time I met Mark, he told me it would be just great if you could just tell me when is it going to be good seeing, average seeing, and poor seeing. That's all he wanted to know. And I think we still always want to know, but that's where we're trying to figure out, and that's where we can get everything else in a simplistic term and knowing devices, but understanding seeing has been proven to be difficult. So what's seeing? It just in simplicity, I'm just going to say it's the incoming light wavefront. It's distorted by a variation of the refractive index in the atmosphere. It's a function of density, temperature, and sometimes moisture. It's seen through that pieces of blurred or scintillating image. Typically measured in arc seconds. Actually, I think it's only measured in arc seconds. And average seeing at Maunakea is about 0.6 arc seconds. But I think there's been records of 0.2 arc seconds. This basically shows it in simplistic terms. Again, this is a plane of wave propagating downwards. It hits a turbulent air layer, and then it becomes permeated. And so you get a little bit of distortion. Here's another simplistic way of thinking of it. If we look through this density of this water glass, and I'm looking at this girl over here, it's quite clear on this side where you can see the distortion of her eye as we go through that, just because we're looking through different densities. Same thing here. This is from UCART. The UCART webcam, looking at the road. I showed it earlier, was a little bit clearer, but it didn't have this. This has a layer of ice on the webcam. Same idea. From an astronomy perspective, I'm sure some of you have seen this before. This is how an astronomy and meteorology are linked from a seeing standpoint, from a turbulent standpoint. So if you imagine this is just an island, and there you got site A here, and it's looking at Jupiter here, and another site here, and the air is flowing through from here, and it's very laminar, it's pretty stable, just very calm, just going through. It hits a mountain, and then it creates these little eddies, which is changes in density of the air. And as we look from point A to Jupiter, it looks quite clear. But as I go through that same turbulent air mass, and I look from point B to Jupiter, it ends up being quite clear. Just an example of that from the astronomy perspective. This is, and I don't know what that means, but. So this is in 0.1 arc seconds, quite clear, excellent seeing. But I'm not sure, well, hopefully this will come off and you guys can see it quite quick, but it's blurry to me no matter what. But just that's because of my eyes, but 0.5 arc seconds, going to 1 arc seconds, and you should be able to see that it's getting gradually more and more blurry. And so this is 1.5 arc seconds. Obviously, we prefer the image on the top, which is our 4K resolution, versus our standard definition on the bottom. We want that. That's what astronomers are shooting for. And to be able to tell them when is it going to be like this versus like this, they can adjust their scheduling accordingly. Fortunately, we have well, Mark has installed this MCAM, which is basically what allows us to verify our seeing forecast, because they have a mass profile which creates the turbulence, shows what the turbulence is like throughout various layers of the atmosphere. This first graph shows it 0.5 kilometers. I think it's 1, 2, 4, 8, and 10 kilometers of the atmosphere. Shows where the turbulence is occurring. This here will show us what the total seeing is, and from the blue is the free atmospheric seeing. So basically take all of this and you get the blue. And then the dim, which is the red, shows us what the turbulent seeing is from the ground. And we use all of our forecasts and we verify it according to this. Now this has some limitations too, because it's situated between Gemini and CFHT. So you see where it's situated is like right in between here. So if the wind is coming across the observatories, it can create its own local turbulence. But it's the best we got, so we'll use that right now. When they're forecasting seeing, it basically comes down to two things. It's simple, but it's not easy, like everything else. It comes down to forecasting the boundary layer, which is between up to 100 meters, and forecasting what's going on in the free atmosphere. And I'll kind of break them down a bit. This here is a histogram of the GFS summit level winds, so 600 millibar winds, versus the night of seeing less than 0.9 seconds. Remember I said that earlier, average seeing in Maunakea is 0.9 seconds. Well, this is basically saying when is seeing great, and map it against the winds. And you recall that I also said that some of the winds are pretty well handled by the GFS. So what we end up having is a typical bell curve. And we have our maximum right in this area, 55 to 5. So this is wind speeds in miles per hour, 0 all the way to 20. The number of nights, 0 all the way to 60. So this is 50. So right in this area, 55% of our time, we're getting, that's when we get a we get a gradual drop off this way and in this direction. So this ends up being our kind of like our sweet spot where we like, and we receive besting when the winds are between 5 to 10 miles an hour. What we have up here, greater than here, the 10 miles an hour, we start to reach into this, what's referred to as bonding layer turbulence. And then here, below 5 miles an hour, we get this thing called thermal bubbles. I'll talk about each. This is the same thing, same graph, just showing standard deviation. Basically, what we're seeing is that in the lower wind speeds, we're getting a larger standard deviation or greater variability. And then up in this area, same thing, greater variability and our best chance for less variabilities in the middle. What we are finding is that winds above 12 miles an hour, we start to really get into this boundary layer turbulence. It starts to stir up things going on for the sun, and the steam starts to degrade. When we get into 20 miles an hour, we end up having forcing. Above that, you know, they'll just do something else because the steam gets awful, and they don't even work on going through that obstacle with it. In this 4 to below 5 miles an hour, we get this thermal bubbles that radiating heat from different objects, and it ends up having just little pockets of air that would end up, this is what we're hypothesizing. And then it produces this like almost like ground layer of boundary turbulence, where different densities of air mass come over the telescope and then creates a little bit more turbulence in there. And it can contribute to poor or bad steam or even large standard deviations in steam. Occasionally moisture plays a role, mostly because of rapid. Now that's another hypothesis too, because we don't have many cases to document this on, or to go back on. But I think it's due to rapid changes in temperature of evaporative cooling. It doesn't occur very often, and it's very hard to anticipate. So this is just an example of boundary layer turbulence state with that strong winds. So it's that same graph similar graph that I showed. So this is the dim in the mass as a function of time for one particular night. This is in September 2017. This is a meteorogram. So this graph is the temperature. This subplot is the humidity, pressure, and then this is the wind speeds. This is what of particular interest, and this is the wind direction. Basically, the winds start out really light and then pop up into the 20 miles an hour. And what we end up seeing is steam response. What we end up finding is steam response to that by degrading throughout the night, and turbulence increasing throughout the lower portion of the atmosphere. The same can be said for very light winds, which I was referring to. So this night starts off at dead winds, 0, nothing. There's no winds, but you can see the large variability in steam going on in this area, and in the free atmosphere, which is in the fluid, steam is great. There's hardly any turbulence going on, but there's a lot of turbulence in that lower level, and we end up getting this large variability. As the winds pick up, steam improves, standard deviation drops. This is somewhat typical of what we see. Here's an impact of example of impact of moisture. So right in this area, we see a lot of little spikes in steam, and right around there, it correlates to jumps in humidity and rapid cooling of the air mass. And what I'm thinking is that we have a turbulence, inversion right over here, and clouds popping in. They evaporate, they cool through a detrainment, and they end up distributing these little pockets of air masses that disrupt the density of the air, and it creates all these variabilities. The other known synoptic environment that produces the modular turbulence is mostly westerly jets or troughs that drop into the over us. It happens typically in the winter time. like something like last week or even today. I mean, not it happened briefly this evening, but over the weekend we got all those drops that moved through, and it just kicks up the wind. And there's no point. Even if the moisture wasn't in there, winds are too strong. It's going to kick up onto the turbines. Deep ridges can also do that. Ridges being anticyclones or high pressure, however you want to refer to it, they can move through and really increase easterly winds and create the modular turbines. Obviously, tropical cyclones and storms, even though they do their warm core system where the height the winds decrease with height, it still can produce strong winds after the sun. And then cold fronts are another one. Fortunately, forecasting modular turbines is relatively straightforward. It's anticipated well through the GFS. Once I know winds are above 20 miles an hour, it's like, okay, we're in course. There's no point. 30 miles an hour is bad. We're pretty good about that. And we know that the greatest potential for great seems between the 5 to 10, sometimes 12 mile an hour range. Once we can determine that, it's about forecasting the free atmospheric scene. That becomes critical. And it's actually the most trickiest because it's not simple. It's actually quite complicated, and there's quite a bit of loops. This is a histogram here that shows the number of nights all the way from, and what is the scene. So basically, I have the scene from here from 0.2, 4, 6, and the number of nights that it was recorded. And so this here's the dim, and here's the mass. So basically, free atmospheric turbulence and what is the turbulence throughout the atmosphere. And what we're seeing is the average. Again, average is about 0.65 arc seconds. It's actually lower than, I think I average 0.72, but it's 0.6. And then down in here, it's 0.4 arc seconds. So the contribution from total scene is roughly half. But what ends up happening is that the free atmospheric scene, it's rarely above the median scene. It's rarely above the average scene. Only 16% of the time is it greater than 0.65 arc seconds. But it still accounts for roughly half of the mean scene. So in general, what we find is that the free atmospheric turbulence is usually based on wind shear, both vertically and horizontally, that becomes a chore. Because if you can imagine a jet isn't just a flat plane. We refer to a jet as like a westerly jet. It's actually like a tube of air going through the atmosphere. So it makes it challenging to try and figure that out. And then there's changes in potential temperature with height. So what we're finding with wind shear, both horizontal and the vertical, sharp horizontal shear can produce eddies that disrupt scene. Let me see. Okay, so real quick, and I'll go back to that one slide, but the islands are situated right here. And this yellow means, so this is 250 millibar winds. It's going in this direction. And the yellow here is roughly somewhere 100 miles an hour up at the uppers. When I was first on to here, I was told anytime winds is over 100 miles an hour, you're probably getting strong shear, you're gonna get a poor scene. That's just the way it is, because that's how we were told. And so I'm going to come back to that in a little bit. And what we're finding is it's not quite that simple. And it also relates to, back to this, not just what the winds are doing as you go up in the air, but also what are the changes of the air right along the horizontal wind creep. And so what we're finding here is that if you're getting strong shear, meaning the winds start light at the surface and veer and or increase with height, then you're probably going to get some sort of turbulence in the atmosphere. When you have winds going this speed and winds going this speed, this one turns to take over and get these little eddies that fall. Same thing along the horizontal. This one's traveling at this speed, this one's not traveling as quickly, so you're going to get little eddies that go along the side horizontally, which can produce things going up the surface, up in the free atmosphere that affect scene. Now, we also have to take into account the changes in potential temperature, which is basically the stability of the air. What is it doing? Are air pressures rising? There's a lot of things that goes into this. Is there a temperature inversion, which means does the temperature increase with height, which is counterintuitive. Most temperatures should decrease with height. So I don't know, you go at bottom of Maunakea, you go to the top of Maunakea, decreases with height. Well, there's times when the temperature increases with height. And if that's located next to the dome or above the dome, that you could create changes in density, which also affects free atmospheric seeping. Triple pause is another issue on its own. It goes increases with height, and it is an inversion, but it's negligible since it's so high in the atmosphere. Its impact on seeing is minor. But the areas of instability can produce sharp changes in potential temperature and the density of the air mass, creating turbulence in the free atmosphere. So what I've done is I created this graph that I use pretty much daily to forecast forecast seeing. And this graph here depicts the potential temperature, changes in potential temperature with height and time. This is time, and then this is height. So 600 millibars all the way to 200 millibars. 600 millibars summit, 200 millibars roughly the height of the troposphere. And so we get a change in what is it? Is there a drastic change versus time or height? And what is the wind slope? And I can use this to look at both wind shear and the changes in potential temperature. So this is that same graph right there, but I'm looking at it at this time, wherever this dotted line is. And what we're seeing is you get this, what we're finding is this large change in potential temperature where it goes from, nothing, and then it's just really sharp, and then it goes back. And what we find is that it contributes to poor bad seeing, roughly right at that level. This is at 8 kilometers, and it ends up being right in that area. And we get these sharp changes, produces really poor seeing. This is 0.8 arc seconds roughly, and we're getting a lot of variability in there. If we look at the 250 millibars at that same thing, the winds are relatively light. Remember I showed you that one where we had a lot of yellow streaming through here, we only got blue, which is only about 20 to 30 miles an hour. And then there's a wind shear, like the moderate shear. So we're seeing that the sharp changes in potential temperature contributes to poor seeing. Conversely, I have the same graph. Now we're looking to this line right here. I know, sorry, this line's a little bit dimmer, but there's hardly any change through that one time. And we're seeing a relatively stable, seeing hardly any changes. There is some shear, moderate shear, like I said, like we're looking at, the islands are here, engulfed in yellow. Strong wind aloft, but there's hardly any shear going on in there. I mean, there's hardly that much variability. So it ends up being more affected by this change in potential temperature. So what we know is that there's the known conditions for, potentially excellent seeing is when we have what's known as the upper level ridge sitting right above us. And then it creates this light uniform winds, and also light, actually what end up seeing is this light uniform cirrus clouds. Uniform flow in the free atmosphere also has a great potential for great seeing. So does other conditions such as deep uniform flow. But all of this doesn't matter unless globular turbulence is minimal. And like I outlined previously, that depends on what the wind range is. So knowing if it's in the 5 to 10 mile an hour wind range, as long as we're in that, then we can look at what the free atmosphere seems like. But if it's above that, then that trumps off, and we're looking at that, of course, depending on where we're at on that scale. So here's an example of great seeing. Here we are, right here. It's 250 millibar winds, and we're in what is situated as known as a anticyclone or deep ridge sitting right over us. Winds are right at about 10 miles an hour, and we're hitting at 0.3 arc seconds. I'm not quite sure what that's all about, but it's still excellent seeing for this this time. And then if you looked at that same graph that I had, the change in potential temperature at that time, there were small changes in there. Now, I showed this graph here previously, and we were socked in with yellow, and I said, I would have said, okay, that's going to be probably a bad night foreseen. Well, we end up seeing it's right in this, we end up finding it's right along this line. We're seeing pretty much a laminar flow, very steady increase with winds at height. And we're getting a laminar flow and we're getting great seeing, less than 0.4 arcseconds, especially right in this area. So it's not that straightforward where that is. And what we're finding is that if this jet is large enough, where there's a laminar flow existing both vertically and horizontally, then there's not going to be that much changes in the atmosphere that will affect steam. It's basically a summary of that. This is uniform flow, potential for calm skies, shear potential for turbulence. We get constant potential temperature, calmer skies. Changes in potential temperature, turbulence. Now the thing is how to balance them all and trying to figure them out and where we are. That's where the problem becomes. If you got part of this, you got part of that, and that's where the experience and intuition comes into play. That's basically that same thing. This just shows the distribution, monthly distribution of grazing as a function of months. So this goes from January. If this is more for curiosity sake than anything, but this is kind of like climate for what Fritz was talking about. We've done this over maybe not climate change, but this is what shows what it's like. This is taking 12 years of data and dumping it in and basically showing that this blue line here shows 1% of the time we get excellency. Green is average, and then this is poor and bad per month. So in this area, we see our best seeing is in June and maybe even parts of September, and that's because of the march of the ridges. The ridge tends to march over us during those periods, and then retreat northward as a subtropical jet builds us over us in this area, and then as the subtropical jet recedes, we get the ridge to bounce back over us again. And it's just the way that the changes over the years, throughout the year. Winter has the highest probability of front, strong winds, poor seeing, bad seeing. Summer months have the great, but unfortunately, we have less light during that time. So in summary, my job is to consolidate and maintain the weather products for the Maunakea observatories through the Maunakea Weather Center site and issue the forecast. Like how I wear a lot of hats that is not seen, but it makes things interesting, not just forecasting for the mountain. In addition to forecasting the key summit variables and conditions for turbulence forecasts, that's actually quite unique. I don't think they do this anywhere else in the world. I think Maunakea is the only place that does it, and it's a complex value that's difficult to quantify. My partner, she got a lot of credit to. Tiziana, she keeps constantly tweaking her model to see where we can improve our forecasts, and she does that through an equation that I didn't go through at all of here, and it kind of bores me a little bit. But nonetheless, she does a lot of work on that to see where all the problems are occurring and how we can fix it. Anybody got any questions?
You talked about those older radar 88s.
Mm-hmm.
Could they relocate them where they'd be a little more effective?
It'd be great for over here. I mean, if you put it in Hilo and point east, that'd be awesome. But then they did that for a specific reason, so that the one in the south can monitor the tropical cyclones that are coming through, and the one in the north can monitor the mountain. Problem we have is in the shadow, so colder and Hilo kind of left. Yeah, so I mean, that'd be great. I would assume that in the next generation of radars, they would do a better job. I don't know.
Okay, just curious.
Yeah.
So who gets better saying, Maunakea or the mountaintops in Chile?
You're asking the wrong person.
I know the answer.
I was just trying to see if somebody more knowledgeable than me would know. But okay.
Well, along those lines, actually, is there any comparable sort of work that's done in Chile? I mean, this stuff is done on Maunakea, so you guys are so advanced. How far behind is, I mean, I think Chile does this sort of.
There was talks at one point about expanding our service there, but it just kind of stalled. I don't know what was going on. No idea how come that didn't proceed. Part of it is Myanmar was short of a radio leader, and they were actually talking about expanding to Alabama as well. So we would have to. It's kind of, this position is quite unique in many regards because, in addition to being a meteorologist, programmer, system administrator, data manager, then Tiziana, she does the exact same thing. She wears a lot of hats as well. Now we're going to expand that for Chile. You can find someone that is kind of, it's difficult. But I don't see why it can't be done. It's just resources are getting right now. I think that was a part of the problem too, the timing of power went down. I think it went down in 2009, expanding resources, and we all know what happened in that time there.
You mentioned running your own mesoscale models and also doing a more targeted version of the GFS. Do you guys run that locally at the university here or in a cloud somewhere?
No, we have a cluster we maintain, and that is a issue.
Is that a pared down version of all the global data, or does it piggyback on the current GFS run?
Yeah, it takes the current GFS, but obviously not all of it, just whatever it needs to create that model.
How far out do you have to look when you're doing 7 days? Spatially.
On which one?
On your
the mesoscale model only uses out to 60 hours.
okay.
Yeah, but the GFS post out to 384 hours, but I rarely go above 7 days. Even that, I wouldn't trust too much. Actually, it's gotten better over the years. Like this rain that we're getting right now, they forecasted this from last week, Thursday.
Do you feed your run back into the global model?
You mean my forecast?
No. Your
Or mesoscale model?
Yeah.
No.
Okay.
Yeah.
The wind forecast seems to get more accurate as you get closer to the day. The 5 day out is usually not as close as the day of or the 2 days.
Right.
The winds are more difficult to handle than humidity and some of the other things, it seems like.
Yeah, probably. Recently the winds have not been well, it's hard because sometimes it doesn't handle very well where it positions everything. So subtle positions means sharper or tighter gradients.
I'm trying to forecast 1 cubic kilometer of airspace.
Right, and so just subtle differences will create. It's the same thing about forecasting a hurricane. A hurricane takes one little drop, one little turn to the north, and then all of a sudden it misses us. It could have turned north way in the beginning, but if it missed that part in the beginning, then it's damaged. It's very subtle changes here affects there, and even just subtle movements will create different stuff.
I have one that's a little bit more serious. Have you and/or your team noticed any long-term, like year-over-year changes in the weather, from Maunakea?
No, I noticed it mostly from a potential perspective, from over the 5 or 6 years, but it tends to go along like a wave-like pattern almost, where 1 year is which follows in, so so this year we're in a phase, so it tends to be wet. So I haven't noticed it being particularly crazy, but I did notice the winds. They're a little bit on the lighter side relative to where in 2003, when we had like 3 episodes of 100-mile-an-hour winds. I haven't seen that, you know. 350-mile-an-hour wind, I mean, 150-mile-an-hour winds in 3 times in 1 year. It actually in 2 months. You know, I haven't seen that yet, so perhaps it's there. I don't see it. I mostly see the March of the season, so I mean, you know,
Is 150 the maximum wind speed measured on the summit? I saw 170 somewhere, but which is accurate? Do you know?
It could have been. I don't know. I mean, it doesn't really matter after that point. I'm not sure.
Yes, every.
I just pulled that figure out of my head. I remember that was in 2003. There was 2-3 episodes in a row, and it could have been, and it could have been just gusts, you know. I wouldn't surprise me at all. Yeah.
All right, one more question and then we'll.
So as an astronomer, we always look for the 5 p.m. Forecast. You've been doing this for over 15 years. So you have never so when you're sick, you've never been sick from Monday through Friday. So I'm just curious, who takes over if you're on vacation or whatever?
Yeah, Tiziana takes over, and she's pretty good about it too. But me and her have a joint. But if I'm sick, it's not that hard. And if you work at home, you can do it. You know, so unless you have the food and dying, you know, then it's not. Most of the time, I'll just take care of it.
And so, as a follow-up, are you training anybody?
Well, that's also the direction we're thinking about going towards. If we expand to we would train somebody to take over. That's always been part of the future, but we just never been able to, I don't know, for whatever reason. You know, getting somebody to actually be here, but now that we can do remote forecasts, you know, I mean, everybody does it already, but you still kind of got to know what's going on here. And so that would be ideal, especially.
Well, thank you, everybody, and thank you especially, Ryan, for coming tonight and doing this.